Hey there, math fans. Dr. Andy Lovelace. What are all these partial derivatives about? Why are we doing it? So here we have this surface. It has a couple bumps, as you can see. It's given by those equations, 1 minus x to the fourth minus y to the fourth, and all that messy stuff. I compute the partial derivatives. I set them both equal to 0, and I can't really solve that nicely. But I want to make up a random example like this to show you that it's still applicable here. If I have some sort of function, I can just keep going. This one I put into a solver. I said solve those equations. So I still had to be able to do my partial derivatives. I computed the second partials. And if I didn't, now I can see in the picture, it's weird that there were 3 solutions. What's going on? It tells me where to zoom in. I thought I would just use some of the visuals I've been making to give a quick little fun with partial derivatives discussion and try to keep it short this go around. So we have these 3 points to consider. The partial derivatives are measuring the slope and the concavity around any given point. And I talked in a previous video about these so-called directional derivatives, all these other slopes. So what we really want, if we're at a peak or a valley, and I'll go to one of these points or close to it. Let's go way up to this one over here. Let's go back here. So if you're up at that peak, if I can get there, you have this fact that the slope is 0 in all directions. And if you can see the picture, then you can also see it's concave down in all directions. Those second derivatives ultimately tell me this, and I'm going to prove it in another video. If anyone cares, let me know. But it's concave down in all directions. Okay, so what I wanted to do is show you this other visual I've been toying around with and use it here. So here's the same thing. I've drawn the contour map on the ground. If you haven't watched my other videos, I do a bunch of taking the contours and moving them to the ground, which is fun. So now I'm just going to talk about that vector that you see on the ground below where we're at. I'm going to show you a bunch of measurements, and I hope that this gives you a little bit of an insight. Okay, so here we are. Here's our point. I've made it so that I can move this around to whatever point we want to go to. And I've made it so I can move this around so I can look in any direction and figure out the concavity and the slope. Now some of that's beyond this course, but I thought this would be interesting. In addition, I have it computing the d, the f of xx, the f of yy, and the mixed partial at each of the points. So let's go to one of those points. Let's go to negative 1.2. So x is negative 1.2, so here, and y is negative 0.8. So right there on that point. I'm close. So if you look around that point, look at the slope. The slope should be 0. It's close to 0. The concavity is down in all directions. Let's let it go. We'll do the same sort of rotation that you're seeing. I'll speed it up a little bit. In that picture on the right, it's concave down in all directions. Let's also look at what the d value is. Notice the d value is actually positive in the second derivative test, but notice the mixed partials are both negative. So if the d value is positive and the mixed partials are both negative, it means you're concave down in all directions. Again, I'll explain that in a proof of the second derivative test. If you're interested, let me know. But that's basically what's happening. So there's a little signature of that. Let's go to a different point. Let's stand over here at this point. This is one of the other points we found. The slope is 0 in all directions. So we can move this other one, try to get over there as well. Let's see. So keep moving. Taking too long to do this. So I was there for a moment. There, we're close by. And let's look around that point. So now we're going to look around that point. The slope is going to be 0 in essentially in all directions. Let's move it back to start and let's let it go. And we're going to do this. It's concave down in all directions. And notice that this so-called d is positive again, and both the mixed partials are negative. So all of those second derivatives are really helping me see that it's concave down in all directions. We had one other point. I think it was somewhere in here. Let me look at it. It was 0.12 and 0.17. So 0.12 and 0.17 about. And now we're standing there. If I move it around, the slope is 0 in all directions. It's concave down. Whoa, now it switched to concave up. And now it switched to concave down. So this D and the mixed partials and all those things are giving this information. You can see it's concave up one way and concave up down the other way. So even without the D, I would have known this is what we call a saddle point. The interesting thing is those are the only points. And I think the work algebraically we had to do was very minimal to find out that this kind of interesting, unusual shape has 3 points of interest in this way. So I hope that gives a little insight into what we're doing with partial derivatives. I've also had fun seeing and playing around with this. Let me know if you find this interesting. All right, thanks.